We have reached the end of our module guide videos. We're focusing on module 28, the goodness of fit module. Now, a goodness of fit test is actually a proportion test that deals with multiple proportions. When we're talking about what a goodness of fit test, it determines whether or not a distribution of categorical variables in a sample fits a claimed distribution in the population. This example on page 188 talks about M&Ms. Now, the Mars company actually published or used to publish the distribution of M&Ms in each bag. So for each type of M&M, like whether it was a Valentine's Day or if it was peanut or caramel or pretzel, they would put the distribution of what the different colors were. There was supposed to be like 13% brown, 13% red, and so on. And so one of the most common hypothesis tests run in statistics classes is to take M&Ms and to see if the distribution matches. Now, these are proportions. They're not averages, they're proportions. And we have calculated proportions before. We've done confidence intervals for one sample proportions, we've done confidence intervals for two sample proportions, and we've run hypothesis tests for one and two sample proportions. This is not just one or two samples, though. We're dealing with 5 or 6 different values that we're doing here. So instead of running a whole bunch of like 30 different proportion tests comparing brown to red, brown to yellow, brown to blue, brown to orange, brown to green, and so on, we can do one hypothesis test where we're saying either our distribution matches or it doesn't. And it's a little tedious to write the symbols for this, so we're just going to go ahead and write things in words. So our null hypothesis is that the color distribution for plain M&Ms is what it's stated. 13% for brown, 13% for red, 14% for yellow, 24% for blue, 20% for orange, and 16% for green. The alternative, and this should be, that should be an A there instead of a 1. Some statistics books use HO and H1 for initial and first, but we use HA. The alternative hypothesis is that the distribution is different from what's stated. And that can happen if brown is off, or maybe the yellow wasn't right, or one of those colors is off. It doesn't mean that every color has to be different. It just means that one of them is different. Question 2 talks about the learn by doing from page 188. We've got stacked bar charts on the left, which are called ribbon charts here. I like to call them stacked bar charts. And then we have tables on the right. So we have these observed counts here in the yellow and expected counts in blue for the random sample 1 of sample size 300 and the random sample 2, which is also sample size of 300. Now, what's going on here with all of these calculations is we're taking, let's say, 0.16, which is 16% of green of the 300. So we're calculating what 16% of green is to see what we would expect. If we had a bag of 300 M&Ms and 16% should be green, that means we should have 48 green. If we had a bag of 300 M&Ms that had 13% brown, then we would expect to have 39% brown. So that's where this expected is coming from. You're taking your sample size and you're multiplying each of those proportions to get what you expect. And then these observed counts are what were actually in the bag. Which sample do you think varies most from the null distribution? And the way you can look at this is you can look and compare the observed versus the expected. How many were close together and how many were far apart? Well, in this sample here, 39 is 39. That's pretty close. This is a difference of 5. We've got a difference here, but look over here is a pretty big difference. So you want to compare and see between sample 1 and sample 2, which one was closer to the actual percentage of what we were supposed to be. Now, I think that sample 1 appears to deviate more from the null because the observed counts are farther away from the expected for every color. We're going to go ahead and continue thinking about how to measure how far the distribution deviates, and we're going to touch back on something that we did earlier on in the semester. One way we can measure this deviation is to find those differences. Like I said, 39 was 39, that's a difference of 0. Let's calculate the differences and see what happens. Now, we're going to first calculate, and then we're going to add up these different differences and see which one has a larger difference. So I want you to calculate, do the observed value minus the expected value, and write that in the third row. Come back when you're ready. Okay, I have my differences here. What I'm going to do next is I'm going to add all of these values for sample 1 and all of these values for sample 2. Okay, 17 plus 5 is 27. Negative 10, and negative 7 is negative 27. This sums to 0. Negative 5 and negative 4 is negative 9. 4 plus 4 plus 1 is 9. Negative 9 and positive 9 is 0. Based on this calculation, our zeros match, and so it looks like both of these samples are as equally variable, but that doesn't really work. So did we get a larger deviation for sample 1? No, they both equal 0. Maybe you remember calculating standard deviation back in the day when we were talking about variance. Simply adding the differences doesn't do anything for us. And remember, when we were doing standard deviation, we squared and then square rooted to handle the negative sign. You can also do this with absolute deviation, which took the absolute value. That's something that you can do. This is what we're going to call a chi-squared test statistic, what we're going to do now. And it's chi, not chi like t, it's chi-squared. And we use the Greek symbol chi. Now, in this formula here, it basically is taking each observed value minus the expected value, what we did above, square that, and then divide by the expected. And then we sum all of these values together. Now, StatCrunch is going to do this for us. But if I was going to calculate, let's say for this first value here, 56 and 39, okay? I observed 56, I expected 39, I square that, and then I would divide by 39. And then I would move on to the next value and the next value, okay? Now notice that I'm not square rooting in here, so I'm not getting back down to a smaller number. I'm just adding up. So the larger your chi-squared value, the larger variance that you have. A couple of things about chi-squared before we move on, since StatCrunch is going to do this for us. If chi-squared has a large value, there's a lot of variance. But what happens if every value matches what it should? Then our chi-squared value would be 0 because our observed value minus our expected would have no difference. A chi-squared distribution is right skewed. It's not symmetric like the normal model. It starts out heavily right skewed, and then depending on your degrees of freedom, the distribution becomes a little bit more symmetric and shifts to the right. They're using degrees of freedom R minus 1 here because we're talking about categories minus 1 rather than sample size minus 1. And our p-value is still the probability of correctly rejecting the null when the null is false. The probability of our chi-squared value being larger than the number, given that our distribution is what we expect, we're going to use StatCrunch to calculate these values for us. But remember, you want to do your state plan do conclude. You want to identify your hypotheses, you want to state your alpha level, you want to check your conditions, you want to run the numbers, and then you want to make your conclusion statement. Let's go ahead and do this hypothesis test now. I want you to see how far you can get in terms of writing your, checking your conditions, and then we will go from there.